Let's apply the Nevada equation, the steady state condition, Gauss's law, and Ohm's law to answer some questions about current carrying wires. There must be an electric field inside a conductor to drive a current through it, but that electric field must be generated by some charges located somewhere. So our first question is, where is the excess charge that is creating the electric field that's driving the current? Is it in the interior space? Let's check by applying Gauss's law. So imagine a Gaussian bag embedded entirely inside the conductor here. The electric flux can be evaluated by applying Ohm's law. If this is an ohmic conductor, then we can replace our electric field at any point inside by the current density J at that point divided by the conductivity of the material at that point. So the flux integral becomes the reciprocal of the conductivity times the current density, like so. And if our medium is uniform, then that is to say, if the conductivity is the same at all points on the surface of that bag, then we can pull it out of the integral. So conductivity comes out. And at this point, we're looking at the closed surface integral of the current density dotted with the little surface area patches at every point on the surface of our Gaussian bag. Now, according to Ohm's law here, our current density vector is parallel to the electric field at all points. So, over at this point here, our J vector would be parallel to the field, and over here, our J vector is parallel to the field. So we'll have J dot dA vectors here. That dot product at that patch would be negative, but that dot product at this patch would be positive. So this represents some current entering into the bag through that little patch, J dot dA, and this would be some current exiting the bag through that little patch, J dot dA. Since by definition, the current passing through some little patch or window, a tiny amount of current passing through some tiny patch is related to the current density vector at that point, like so. So this closed surface integral then becomes the sum of all the current entering the bag and all the current exiting the bag. So 1 over sigma stays out front. When J dot dA is negative, that's current entering the bag. So we'll have negative the total amount of current going into the bag. And when J dot dA is positive, that's current exiting the bag. So plus the total amount of current exiting the bag. That's the result of this closed surface integral through the bag. And in a steady state, no charge may be building up inside the bag. So the current going in has to be equal to the current coming out. So this sum must be 0 to prevent a charge buildup from occurring there. And so our argument is that in a steady state flow, there is no net flux through a Gaussian bag of any shape inside the conductor. And if there's no net flux through a Gaussian bag of any shape, then there must be no charge enclosed inside that bag. So previously, we've always argued that the charge enclosed anywhere inside a conductor in equilibrium was 0. Here, we are not in equilibrium. We're in a steady state flow. But by a similar Gaussian argument, we're showing that even in a steady state flow, there is still no charge enclosed inside any Gaussian bag inside your conductor. Which means then that the volume charge density at any point inside the conductor, which will be the sum of the volume charge density of the free electrons plus the volume charge density of the ions, which can be written as the charge of an electron times the number density of electrons, plus the charge of each ion times the number density of the ions. That density has to be 0 by this argument everywhere inside a steady state conductor. So, conclusions. In steady state flow, we've just shown that the excess charge that's creating the electric field, it cannot be in the interior space. There's no net excess charge in the interior space. So the excess charge that creates the electric field must therefore reside on the surface of a uniform conductor. That's the only other place it could be if it's not in the interior. And therefore, the density of the sea of free electrons cannot change unless the medium changes. That is, we need the number density of free electrons to be the same as the number density of ions everywhere inside. The essential consequence of this is that it will not be possible to sort of compress the cloud of free electrons into a higher density if the number density of the background of ions does not change. So we can't sort of pack more electrons into a volume than there are ions. They have to remain a one-to-one correspondence, because if they were out of balance, there would be a non-zero net charge inside some Gaussian bag. And for